Hi everyone, thanks to the organizers for having me here. Yes, I'm under the weather, but it's okay. I can speak. Not on Friday I couldn't, so it's good that I was bound to speak today. So today I'm going to be talking about spatial data. This is very an overview, a little bit about my own journey, and also an invitation for everyone to start exploring spatial data using open source tools. So this is my first amazing slide, so I'm lifting from XKCD. So before, there was a barriers to entry in order to do spatial data analysis. You have some sort of domain expertise. So you can go to departments of geography, much into, building maps and exploring maps. But now with open source data and with all the libraries that have been produced for lots and lots of people and lots of time put into doing that, anyone can actually go get data from any different source online and actually mesh that with your own data and start asking very interesting questions and being capable of answering those questions. So that's why before we would go like, make me a map or make me an analysis. And now we can answer, well, make it yourself. So now we can do it, and we can now tell the computer to do it for us, and it's quite straightforward. So a little bit about me. So I work at Halo London, where we basically connect customers with cabs. You can find me on Twitter. It's probably the easiest channel you can reach me at. I'm terrible at emails, so Twitter is where you find me. And this is actually a trip I took on one of these days on one of the black cabs. So we use maps a lot at work and on the day job, and in fact that's why we have such a huge amount of spatial data that and because we're a small team and we have to look at different types of data and different types of events. This is something that we actually had to teach ourselves how to do. So this is the plan of this talk. So first I'm going to give you a bit of motivation as to why we should care, basically. I'll give you an overview of spatial data, talk to you about formats and tools, and then give you some examples because, of course, that's the interesting part. And finally, some links and resources. Also notice I'm looking in that direction because I don't have the slides in front of me. So it's not because I want to ignore you guys. What's spatial data? Well, we all have some intuitive understanding. After all, we live on this planet. So if you go on Google and just type spatial data, well, you'll find all this, shitloads of results, and you'll find a nice definition, also known as geospatial data or geographic information. And it's the data or information that identifies the geographic location features and boundaries on Earth. So basically, you just get some data, it has some lat longs, and there you go, you have some spatial information. And usually, these are listed as collections of data with more than one dimension, and they're expressed as coordinates. So for our purposes, if you've ever used Google Maps, then you know what they are. So that's what it is. So this is where we are. And if you usually look at the URL of the page, you'll find lat longs that represent this point in some projection. So, of course, now we have all this public data online. So I've been playing around with London's TfL feeds, and in particular with their, disruptions and roadworks feed. So you can find all the information about every single possible event that has happened in London for, I think you can query it for some time before today and even to the future because there's planned roadworks. So, for instance, if there's going to be some, celebration or festival and they have to close some roads in London, you can get it from there, and you can learn what are the places that are going to be affected by it. So if you just pull the JSON and then you put in a data frame, you can find some ID. You can find how severe the problem is. You can find what category does it fall in. So if it's an infrastructure issue or if some traffic incident. And literally when it was one of these final football events, so you could find ahead of time something like, if our Arsenal wins, then these streets will be closed and you won't be able to come in. If not, then nothing happens. So this was listed all in within the event. So you have start and end date, level of interest, location, the status, and there's more information. I didn't pull every single thing in. But this is very interesting. And then what happens, you have this information and you usually put it on a map and then you visualize it. So, okay, why did I start looking into spatial data? Well, the day job. At Halo, we need to understand where passengers need cabs, where to send cabs, etc. So in short, we need to understand cities. So there's lots and lots of questions you can make around spatial data in our context, but I'm sure you can also make these questions in all your different contexts. I'll give you some examples. Also, curiosity. We have an increase of availability of public data feeds. And then also, I like maps. And who doesn't like maps? But in any case, we use data every day. So say that if you work on e-commerce and you're usually used to pulling transactions from your database, and usually you'll have some timestamps associated to those transactions, and you're going to spend lots and lots of time analyzing these transactions and looking at time series and stuff, right? But usually these transactions, I mean, if it's online, if you're a global business, there might be some place located to them. You have physical stores, so outside e-commerce, you have positions, and all this, the location of such transactions might actually have meaning. If you're looking into, your log events of your computer systems, this request spikes or anomalies might happen in a specific place. So actually, this is quite relevant. Thing is, we don't spend much time looking at it. And then, of course, now in the age of mobile devices, well, they all have location enabled. And all those events will be sending location of people where they are. And all these events are happening at a specific place. And so there's lots of questions that we might be, might need to start posing in order to understand how people behave. So spatial data in this case is not only for polling people or logistics people or public health people that are usually the analysts that are used to looking at this data, but actually it's relevant for everyone. And I think the main point of this talk is to basically get you with the idea that no matter where you work or what you're doing, this is relevant and you should have the tools that allow you to explore this. So this is a word that is thrown around a lot, so GIS. So this stands for Geographic Information System. So this is a system that would let us visualize, analyze, and interpret data to understand relationships and patterns. Now, why do we care about this? Or why did people care about that? Well, because, in criminal justice, there's spatial criminology. You want to know where crimes happen and if there's areas of incident and how to deal with them, so then you can deploy, your people or the police in a better way or deal with them. Then public health and epidemiology, we want to know where illnesses are happening, where they originated. We want to be able to do something about it. Housing markets, we want to know how they go up and how they go down. Why is that? So then understanding where the different areas in which this happens and try to look at the features spliced by location, it's very, very important. Transport and public services, as I said, you have operations and logistics around that, and you want to make them more efficient. And finally, elections. I mean, everyone saw what happened with the polls this time. And now, actually, an interesting thing is to slice those surveys and results and the actual voting behavior by where it happened and why it happened, and try to correlate the demographics of those places with, vote intentions. So some typical questions in spatial data that arise are, okay, is X location within Y space? So what does it mean? Well, maybe when I identify individuals with specific characteristics that are bound to that specific space. Or you might want to test an hypothesis as to why specific events happen in that space. So this is a typical question. Then, what is the space that satisfies X? So you might have some constraints that define some space, and you want to understand which are all the possible spaces where these constraints are satisfied. And then maybe, for instance, you want to know the values of those features in a space that satisfies X. So, for instance, I want to find a space that, I don't know, which neighborhood in London has the highest percentage of highly educated people? That's a random question. And then you want to know, basically, some other value of another feature in this space satisfying that constraint. Third question is, given a location, where are the closest K nearest features? So given that I'm here, where are the 10 most, the closest pubs? So we want to go after the talk, right? And then finally, another question is, given a bound, what are the values of those features or other features? So these are all typical questions that arise when you're looking at spatial data, and that we want to have the tools to answer them. Now, as mentioned briefly before, there have been some barriers to entry for people to actually start doing spatial analysis unless you had domain expertise. So traditional GIS systems were expensive. So ArcGIS, I have no idea how much it costs the license, but it's expensive. And then their big grandfather open source libraries are written in C and C++, and they're quite, there's a barrier to entry there if you are not, proficient in C and C++ and you're not, understand all the dependencies of those libraries. I've heard that actually they're very, very tricky to install. So now there's lots of open source tools and data resources that enable people to look at spatial data. And in particular, there's great libraries in Python and R that allow you to visualize it and analyze it. So let me now move on to some of the key concepts around spatial data. So of course, there's the issue with the Earth not being flat. So how do we go from a sphere to a plane? So then you have a geographic coordinate system that uses a 3D spherical surface to define locations on the Earth. So you can look at the Earth as if it was a spheroid or as an ellipsoid, and then define coordinates in that spheroid and that ellipsoid. And then this geographic coordinate system will define points on that surface, and will also define the relative altitude. So for instance, the WGS 84 will define also with respect to sea level. And then finally, you have projected coordinate systems, which will be defined on a flat space, and it is always based on a geographic coordinate system. So for each of these, you can find a projected coordinate system that refers to that particular coordinate space. And that's quite important, because if you start looking at spatial data online, you'll eventually have to deal with projections and with coordinate spaces. And typical newbie mistake when you do a map is that, oh, I just pulled this data, I'll just plot it, and then you want to plot another object there, and suddenly you get an empty map, and you're like, what happened there? It's like, oh, they just happen to have different projections. So you need to be very aware as to what these are. So a sphere can be flattened, so the projected data are going to be distorted in shape, area, distance, or direction. So that's why some projections are designed to minimize a specific problem or preserve specific characteristics. So I found this very, very nice image online where you had basically different projections and plots of South America based on all those different projections. And you can see some projections will be designed to preserve angles, some projections will be designed to preserve specific distances. So some are conformal, some are on the cylinder, some are different. So, and depends on what you want to preserve is the one that you will pick. So these are two questions that you always need to ask when you get hold of some data, which is which geographic coordinate system are we using and which projection. And often you'll find that people are happy enough with just a flat projection. You just take the lat longs and you just push through. But that's not the right thing to do in any part of the world or any circumstance. So this is another XKCD comic that you can find. It says, what's your favorite map projection says about you? And it's actually very, very long. But I think it's quite interesting to see what are the different projections, and also to understand how the shape of the different territories change with those projections. So have a look. So OpenStreetMap data is stored in WGS 84 lat long. And then you'll always find this EPSG, basically an EPSG code. So WGS 84 stands for World Geodetic Survey 1984. So this is a geographic coordinate system, and this is a reference ellipsoid for raw altitude data and the surface that defines the sea level. So this treats at the Earth as an ellipsoid. The one that Google Maps uses, I think, actually treats the Earth as a spheroid. So those are two different ones. And then the EPSG is just an identifier, a reference, and this stands is European Petroleum Survey Group. And this identifies the WGS 84 as a spatial reference. So these are very common, you'll find it everywhere, so now you know what they are. And if you're working with UK data, so often you'll find also the OSG V37, the Ordnance Survey, and then the projected coordinates that often are used with respect to this GCS are for this the Web Mercator, and for here the British National Grid. So always good to know these things. And basically what happens is that if we use this, sometimes for the UK, the areas will be slightly distorted. So that's something that one needs to look at. Now, let me cover some of the basic types. So I know that there was this very interesting tutorial going on Friday, but I'm still going to very quickly review them so we have them fresh in our heads. So we are most used to dealing with scalar objects that we can do operations on. So we have lots of numbers, and then we add them up or subtract them up or do lots of interesting things. But here, most of the time, we'll be dealing with geometric objects. So here you'll have some basic types like point lines, polygons, and then you can have collections of this. So you have a collection of points, collections of lines, or collection of polygons, and then upon those polygons you can have holes or different things. And finally you have bounds. So this can be defined in whatever library that we were looking at, and I'll discuss that in a little bit of a while. And then once you have these types, you can perform operations. So if you're thinking of polygons, those operations in your mind, you can think of them as the usual set operations. So you can have intersections, unions, differences. You can create a buffer that is like creating like an area around the shape. And then you can also find the centroid of a polygon. So if you have something that is very complicated, you can look for the centroid of that polygon or the centroid of a collection of points. So those are usually defined. And then there's lots of different formats. The most common format for spatial data that you can find is the ESRI shapefile. So shapefile is like a misnomer because it's actually a collection of files. So you can have basically an .hpeak, which is basically the shape format, and then you have the index. Then you have another file that stores all the attributes, the data attributes of that shapefile, and then finally you have some projection format that is stored in this. So if you plot them, they look like this. So very nice shapes. And then you also can have serialized formats like GeoJSON or TopoJSON. So it looks like that. So you have here, all the geometry, and you have all the coordinates of the geometry. And you'll have also some properties and some information about that specific event. And finally, you can have KML, originally developed by Google Earth. The Google Earth project, Keyhole Markup Language. So that is very familiar for online stuff. And that's basically vector data, but we can also have spatial data in the form of raster or pixels. So these are images, and in these images, the geographic location of each cell is implied by its position in the cell matrix. And for the same reason, the cell size will determine the resolution at which the data is represented. So you can only go that small. Usually it's a GeoTIFF file. And here what you can see is, so you have the image space, and this is literally your coordinate space. So you can see that each position will have some value of the cell. So these are often used for data such as like high-speed data when you have land use or soils data. You can also, they're very useful to understand how a feature that can be thought of like a field across a big set of in space, such as temperature or elevation or spectral data. Just when I think of temperature, I think like a scalar field. And also for satellite images and aerial photographs. So that is very well encoded in a raster. And finally, pictures or scan maps. So actually, rasters can be used very well for base maps. So you can have a raster file of a map, and then you can basically visualize points on top of that raster. So and also, I mean, rasters are very good because they're very efficient storing-wise, because they're very simple structures. It's just a matrix with values. So there's lots of different advantages of rasters as well. But for the purposes of my examples, I'm pretty much going to be looking at vectors. Well, tools, as I said, there's ArcGIS by ESRI. I have no idea how you pronounce that in that way, so I'm just using the letters. And this is an enterprise solution. There's the open free QGIS. which allows you to edit, query, and analyze data. So there's some desktop applications that you just load the information and then you can open up and see all those shapefiles very quickly and color them by different things, different values of features. Then you can have spatial databases that have been developed to build queries regarding spatial data. So you can have PostGIS. So if you've used PostgreSQL before, so PostGIS is just an extension that allows you to write geographic queries, or you can use also Spatialite. So in the same way PostGIS is to PostgreSQL, Spatialite is to SQLite. And then, well, as I mentioned before, the granddaddies of the libraries for geographic analysis, GDAL or GR libraries. So GDAL is the Geospatial Data Abstraction Library for reading and writing raster geospatial data formats. So GDAL is for raster and the OGR is for vector. And there's also the GEOS library. It's geometric engine open source. It's built, I think, originally in Java. And this also, basically every single thing that you can find in Python and R that have to do with tools to analyze spatial data are built on top of these libraries. So there's lots of dependencies. Finally, there's lots of web maps and there's lots of integrations between Python and R as well to produce nice web applications using Leaflet extensively or D3 or Mapbox. So if you build lots of web visualization tools on the web, you might be using D3 or Leaflet. And R has a very nice library for Leaflet, so you can do Shiny apps using maps as well. So there's lots of interesting tools that now have been coming up thanks to the availability of spatial data. Okay, so I think this is a good part just to stop. So any questions so far? No?
So we've got 10 minutes until the hard stop. So
okay.
You can either run for the 10 minutes or do 5 minutes of Q&A or whatever you want.
Okay.
10 minutes to the hard stop.
Okay, cool, because this is sort of like half.
Sorry, we had to start a bit late.
Yeah, no, that's fine. So, because of course those issues of when you go to the company and try to get data for a talk get complicated, I decided to just choose public data in order to show you some examples. So, as I said, TFL has great APIs for us to play with and ask questions. So here are all the relevant links. So here just literally, first I'm going to show you some examples in Python, but because I also like R, I'll also show you some examples in R. And then I'm going to explain what are the good and bad things of both and where they're going.
In 10 minutes?
Yes.
That's it, right?
Yes, because I'm not going to really go too much into the code because people can then go and actually look at them.
You can take it easy if you want as
So
well.
here I just imported like the JSON from the API of TFL. And I just look at the very completely random period of time, but you're happy to ask whatever question. I wasn't really thinking of something very specific, but at work we've been doing analysis about roadworks because, for instance, I don't know if you pass through the South Bank, but because they're building the, for people that ride on bike to work, all that road is closed, Kingsway is closed, so that's causing havoc to our cabbies because basically we send jobs to people and usually the ETAs are longer. So then you actually need to start looking at these things in order to become smarter about things. And then here I use pandas because pandas is also nice. And I just pulled stuff into a data frame. And as I said, you can look at all the different types of information you can find. If there's closures, for instance, which category is, when it started, the severity, its level of interest, etc., etc. So this is quite standard stuff. This is how the API looks on the browser. So you can find this type of comments. So at St. James Street between blah, 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 and lots of metadata. So if you want to do lots of text analysis as well, there you go. Lots of fun. And here you can find, like the EPSG 4326 that I told you about, and then coordinates. So you can find all the forms. So what do we do in Python? So what is a standard pipeline? So we use Fiona, this library that allows you to read and write data formats. So this uses OGR. and this supports many vector formats, so ArcObject and shapefiles, your JSON, etc. So the idea is that you read all the different shapefiles that you might have, and then you can build collections, and then you'll use other libraries to start analyzing those things. So once you've read your stuff with Fiona, then you'll use Shapely. So this is a library for manipulating and analyzing planar geometric objects. So it depends on the geos library. So this will allow you to perform operations outside of the spatial database library. So you don't need to go to a PostGIS database, write your queries there and get the information, but you can do all within Python. And then Shapely implements points, curves, and surface through classes. So the documentation is actually really, really nice. So you can go and have a look. So this is how you do a basic scatter plot map. So you read shapefiles using Fiona, and you read the points data. So all the JSON that I pulled in, I just dumped it on a CSV. And then I just reread it. Then here is literally, I have all the, you can find from Ordnance Survey, literally all shapefiles about London, from the border level to the ward level to the tiny, tiny neighborhood level. So every single thing. And you can go and play with them. So, so here I got the London wards, I got them down. So define the boundaries of my map. Then you build a base map using matplotlib space map. So here you read the shapefiles. I'm not going to go into the details, but once you have that, then I literally set up a data frame with all the different word names and create the point objects in map. Well, you can look at the slides, and I tried to comment everything. I might put the notebook up as well, but this is basically just putting everything that I need in a very nice data frame so I can plot it. And here what I do is just, so I just added another column called patches. So I build the patches that I want to draw. And finally I just plot it, and then there's lots of styling there. And there's much better tutorials than whatever I could ever write. And this very interesting links. And you get something like this. So that's a plot of all the roadworks on the period of time that I was looking at in London. So that's a very nice visualization. This doesn't answer any type of question. But then you can start asking like good questions, like, which roadworks actually affect specific areas of the city, which streets are affected, where are the closest streets to where the roadwork is that are affected, etc. So this is just like 101 visualization. Then you can move on and do choropleth maps, which are super popular and you can find online everywhere. So what do you do here? So the pipeline is usually you define a question and the surface density relative to the metric you are going to analyze. So that's like probably one of the most important parts, is like, what is the metric that I want to look at and what is the relative density? And then, for instance, if this is going to be number of roadworks per word, then I have to look at the area of each shape that I'm going to be looking at. So I just add the areas to my map data frame. I just do some count, and then I compute the densities. And then you can define the buckets of your colors. So all the colors. So if it's high density, it will be one color. If it's low density, it's going to be low color. So how do you define the buckets is up to you, but you can use the Jenks natural breaks classification method, which tells you what are the best breaks you can have. And then you just split everything in terms of that bucket factor. And then you can plot something very nice like this. So as we can see, basically, around Westminster, you can find lots and lots of higher density of roadworks compared to other parts in London for the time period that we were analyzing. So this looks really, really nice. But you can also import other types of objects which are not necessarily polygons, but you can have road networks. And so you'll have some collections of lines, and then you can visualize by type of line, type of road. So here I just visualize like primary roads in London in a darker color. But you could basically highlight lines that you're interested by defining some specific question that you want to know. And this is quite simple. to do. And if it's in a pandas data frame, then you can just slice your data frame by whatever it is the thing that you're looking at, and then just you plot whatever is on. And you can also overlay another polygons. So here what I did is every green stuff is the area that is affected on this this data set of roadworks. So this is because there's going to be this huge event in August, like this weekend where basically you can cycle all across central London and go to all the different places. So when I first saw it, I was like, what the hell is that? It's not like the whole London is, going down, but it's more because it's going to be all this area is going to be affected. So something more interesting is actually to do the same map, but for different time periods, so you can see how this changes. So you can do one of those very nice multiple mini visualizations of different maps and see the evolution of those. But here I literally plotted all the boroughs, then all the roads, and then all the little polygons that I just got from the API. So you can think of many, many different things. Yes? Okay. And then, well, there's other libraries. So PySol, which is the spatial analysis library to do statistics. I haven't played much about it, but apparently it's very, very good. And GeoPandas, which is the thing that I'm most excited about, but it's still I'd say in its early developments. GeoPandas is basically builds everything that I showed you before, but into one cohesive framework. So the flow is much more simplified. So you just you build your data frame. So here's a nice boroughs data frame. So and here's your geometry. So this is how it looked like. This was just very straightforward, like boom, boom, boom. So instead of going Fiona, Shapley, and stuff, boom, you have it there. And then you can slice the data frame very easily. So here I did a very silly stuff in which I just say, give me all the boroughs that have less than 1,000 hectares, and then just plot it. And I don't have to do anything, just this short, and boom, it's plot. So it's really, really nice. And you can do intersections and unions, and some of the things you can do in Shapely, but all within Pandas. So this is really, really nice. And then very quickly, maps in R. So if you look at GeoPandas and if you've done maps in R, what you'll find is that it's literally what you already have in R as well. So it's quite portable to go from one of the other one because it's some of the same ideas. So this is a very famous visualization that was done in R. And so you understand the mapping between the Python libraries and the R libraries. What you find is, so SP defines the classes for spatial data. Then RGeo's library is like plus spatial, is like Shapely. So you have all the same functions to operate, unions, intersections, all that stuff. Then RGDAL is like Fiona in some ways. It's just to read I/O on your spatial data. And then MapTools is another nice library. It also has some I/O functions and some manipulation functions. But the nice thing about the SP library is that you have these options like the spatialized data frame, the spatial polygon data frame, and literally you have the extension of the data frame concept to involve also spatial data, and all the standard data frame operations follow. So this is an example. So this is literally the spatial data frame, how it looks like. So you'll find all the different features of the data, and then you have all the information about the polygons. And if you do ahead, you'll find the same listing that you found when I was looking in Pandas, but here this is from the art perspective. And you can do exactly the same thing. This is the same thing. So same type of construction, and boom, you plot it. So it's very, very similar. And well, you can do same type of scatter plots. So I did exactly the same thing. Here you have more or less what I did for Python, and this is just colored by the type of roadwork that it is. So you can do exactly the same thing. You can do aggregation, which is what once it's everything in GeoPandas, you can just proceed in the same way, and of course then it's very easy to produce chloroplasts. So you can using aggregation, you can compute the densities and you can plot them. So other questions you can make. So this is just the shapefile of Hammersmith and with all the streets. And this is a particular area that has been affected by some roadworks. So you can ask questions like which streets fall within the affected area, how do densities of works change with time, what are the closest primary roads that are affected, what is the average number of wards affected by a given roadwork. And then you can combine this with other data sources, because once you have a data frame for this, you can have other data frames for other things, and then you can merge them. And then once you have that, you can build web visualizations using Leaflet, Mapbox, or D3. So TLDR, performing spatial analysis is now more accessible than ever. Open source libraries in Python and R allow exploration of spatial data and mapping, and it's very easy to do cool maps. So these are some links that might be worth your time. So once the slides are made available, just click on them. So there's lots of sources for shapefiles, the Ordnance Survey, some basics on Python's geospatial libraries, some very nice tutorials. I have never used Vincent as a visualization library in Python, but some people like it. So you can also do maps with that. For people that also like R, so there's other links here. And then finally, a very nice book that has come back with lots of different maps. And the bonus is you can also get lots of nice, cool shapefiles for Westeros or for any other fantasy realm that you can think of and do exactly the same thing. So this is a map that I literally just got the shapefiles for the whole Song of Ice and Fire universe. So you have Westeros and Essos with all the cities are in red and yellows are point of interest and all the rivers. And you can do this. So even if your data at your company or day job doesn't involve lots of location information, you can do maps quite simply. So I think that is the end. So thanks.